My prior two videos were showing how to plan an experiment to see if counts of crime were reducing over time and how long to plan to evaluate or collect data or expect to have to do that intervention before you can tell if your estimate is precise enough to be able to tell if your intervention is working or not. This video, I'm going to show you guys how to use that same tool, but instead of counts per crime, you can look at rates per event. So say you purchase cameras and you want to see if those cameras increase arrest rates or clearance rates for crime. So in that example, the denominator is the total number of reported crimes and the numerator is the number of arrests. Or say you're doing training to reduce use of force. You could examine use of force as count over time. So the prior examples I gave on counts were all crime, but it can really be counts of anything. All that matters is if it's distributed according, like approximately Poisson. But a lot of times for use of force, you want to consider a denominator like use of force conditional on arrest or use of force conditional on a police interaction because those can change over time. And so this example is going to show how to do that same sort of planning. It's like, how long do I need to monitor this particular intervention to be able to know up front, okay, I need to spend 6 months collecting data to be able to do a decent study design to see if this intervention is working or not. So here I'm going to go, if you click the proportion events button, here what you can do is similar to before, you basically fill out your information and then it'll give you a nice plot where you can see how long out or how precise your estimate is over time. So imagine in this example where we purchase cameras and we're trying to increase arrest rates. So say we put cameras and we're looking at arrest clearances that are basically in the view shed of the cameras. And on average, we have like a 40% clearance rate, which is probably a little too high for a lot of things, but we'll go with that example for now. And we think that the cameras are going to increase to 45% arrest clearance rate. You can put in your control sample size or treated sample size. And so, unlike the prior examples, these sample sizes can be potentially different. So the control, if you have more control points that make sense to use, you can basically use more. So here we'll put it in as 500 events per unit time, and then treated sample sizes, we'll make it smaller. We'll make this 40 events per treated time. And then you can say the number of time periods, the alpha level. So this by default constructs 95% confidence intervals. You hit calculate plot. And now if we scroll down, you'll see that familiar sort of funnel. And so we think that this intervention is going to increase arrest rates by 5 percentage points. So this is a percentage point increase that we're looking at, or we expect over time. And you can see that the standard error basically shrinks over time given how many events we expect here. And so we would want to do this experiment, do this intervention for around a year, or expect to wait a year before we get a really precise enough estimate to know if it's working or not. Similar to the other plots and everything, you can go show the R code. You can look at the table for the standard errors. And this is using what's called a normal-based approximation to calculate these error bars. So there's a bunch of different ways to do these types of proportion tests, but for planning purposes, this is totally fine. Some of the other tests will maybe have a little bit wider or a little bit smaller confidence intervals here, but honestly, this is good for planning. You shouldn't basically make your planning on a razor's edge. So you basically don't want to do this and look and see, okay, it's only just not covering zero at 12 months. It may be that may be too optimistic, and so we want to go out like a year and a half, so we have a little bit more wiggle room essentially to do that particular intervention. Now, one of the things is here when you have smaller sample sizes, especially in the particular treated pool, it makes it more difficult to identify those percentage point increases over time. And so if you have a smaller number in that treated, you can see that it's a bit wider, and here we have to go out to almost like 20 months to not cover zero in that particular point. And really, you can add in bigger and bigger control areas, but it really doesn't help all that much here. And so basically, this smaller set, this smaller treated pool pretty much bounds the potential standard error. And so depending on what the proportion is and what the size of this treated sample is, there may not be any particular control sample size that is effective in like a reasonable amount of time. So it really just depends on like these proportions and sort of like your minimal treated sample size per period. The last example that I'm going to show here is a little bit more complicated scenario. So in this particular scenario, we basically have this same consistent baseline proportion between across all the different cases. And so I've been talking about areas. So like I gave the example of cameras. It can really be anything. It doesn't necessarily need to be areas. So it could be, say you did training and you're looking at different shifts. And so really in this particular example, we just want that, absent that intervention, we want that control proportion to be approximately the same between the treated and control areas. Now, for a lot of different scenarios, so like the scenario with increasing the arrests or clearance rates for cameras, it ends up being you don't really have like, you can take the average of all your crimes and look at the proportion of arrests there. But in reality, different crimes have very different baseline proportions. So interpersonal crimes tend to be solved at much higher rates than property crimes like people breaking into cars or thefts. And so this next simulation that I'm going to show, you can basically have a more complicated scenario where you can set different baseline rates for those particular crime types. And then you have your treated and control areas essentially. And then you also have the mix of how many crimes are in amongst those particular crime types. So here we have, these don't necessarily need to add up to 100%, but we have more assaults, we have more robberies here, fewer burglaries, larcenies, and motor vehicle thefts. This is probably should be changed a little bit so larcenies are more common and robberies are less common. But essentially this first number gives us the mix of the particular different crime types. This second number gives that baseline solve rate. And so let's up robberies here to 25%. Say the clearances for robberies are 25%, assaults are 35%, burglaries are much lower, 10%, larcenies are probably going to be lower, 5%, motor vehicle thefts, 1 out of 5. And so here the model is a little bit different. We're going to say we think that the cameras help increase arrest rates by, this ends up being what's called an odds ratio, but it ends up being pretty similar to a percentage point increase. So say we think, or not a percentage point increase, but a percent increase. So we think that on average, they're going to increase those baseline clearance rates by 20%. And so to make it a little bit easier, they're going to increase those baseline clearance rates by 50%. So think, for example, we think motor vehicle thefts are going to go from 20% clearances to 30% clearances. Then larcenies are going to go from 5% clearances to 7.5% clearances. Burglaries are going to go from 10% clearances to 15% clearances. so on and so forth. So it's not a consistent percentage point change across each crime type, but we think it's going to be a consistent percent increase. And what this does is it runs a simulation in the background where you can see how long, similar to the other the other applications, how long you need to run that experiment to essentially see, okay, what's my standard error going to be in that particular scenario. And here you can see in the original estimate with estimating 1,000 crimes, so monitoring 1,000 crimes in the end. And so this is 1,000 both. This is 1,000 across both treated and control. And what it does is it just randomly assigns. So we think that the mix is basically going to be 50-50 here. And so what this does is does a simulation to show here's what the odds ratio in our simulation is. It is actually important to look at the bias in these estimates, especially for small n for this particular model, because it can actually be biased here, but it also shows the standard error. So in this particular example, you can see that with that big of an effect, a 50% increase in clearances, we only need to examine around 1,000 crimes to know if it's working or not. You can go ahead and change the total number of crimes, make it more dense or less dense so you can look at, let's say 800, 900, 1,000, 1,100, 1,200. You can up the total number of simulations as well. And just to show it, we'll change the odds ratio. You can essentially just go and add in more and different baselines of different types of crimes here. So let's do something like we'll just add in BMV. Like I said, these numbers here don't necessarily need to add up to 1, but under the hood, the algorithm will just basically distribute them. And so let's say 0.2, and then let's make the clearance rate for this very low. We'll go ahead and run our simulation again, and it does the total number of simulations for how many total n values basically you have here. So you get, it says right in your browser how fast it's going. And so here we'll look at that plot again, and we can see that in this particular simulated scenario, it always ends up covering our baseline of 1. So we'd want to run this again with a larger number of potential samples in our estimate to see how long. And so you would use the same sort of logic as I showed before. But here you would say, okay, so we expect to have around 500 crimes a month. So pretend this ended up being, we want to capture a total of 2,000 crimes. That means you'd want to evaluate or wait at least 4 months to do the evaluation, or expect to be able to tell if that treatment, if those cameras, if that software, whatever you're doing in that scenario, are working.